Hello, everyone. So welcome back to the 2019 Spring Summit. My name is Alexa Darsh. I am joined here today by Zachary Gallipo and Tyler Kaiser. We make up Team Infineon, and we are very excited to tell you about our project today. Our project deals with the System Power Extended Cycling System, the SPEC tester. And if you don't know what that is, that's okay. We didn't either. Basically, it's this huge rack of 60 sites. The rack is made up of 6 neighborhoods. Each neighborhood has 10 sites. Each site has a phase card, and each phase card has a DC to DC power converter. In case you don't know, Infineon Technologies is one of the world's largest manufacturers of semiconductors. You use their products every day, and you probably don't even know it. But what happens with these DC to DC converters is the system runs a high current through them for an extended period of time. The Infineon engineers take a lot of metrics from this test. It's very important, and I hope you all understand this because we're going to have a quiz later. Just kidding, but this is a lot to take in, so I have a metaphor to make it easier. Think of the SPEC tester system as a school. The neighborhoods are like classrooms. Each site is like a desk. The phase card is essentially an exam. And each DC to DC power converter is a student taking the worst exam they've ever taken in their life, kind of like taking the SATs back to back a dozen times. With that in mind, our first motivation for the project was to have a way to communicate with each site. Right now, Infineon doesn't really have one. It's all manual, it's tedious, it takes a long time. Secondly, we needed to have thermal control of the system. Again, they don't really have that, so the temperature isn't consistent, and the engineers don't know what it is. And lastly, because these tests last so long, we needed a very set it and forget it way to monitor them. Nothing that takes man hours, nothing that involves going to each site individually and measuring anything. So our anticipated best outcome, first and foremost, we wanted to have full thermal control of the system from a single computer. We also needed to have a critical status management system. This is so in the middle of the night, if something gets really hot or something goes wrong, the system doesn't just catch on fire and burn the lab down. And lastly, we needed the users to be able to control this in a way that was fairly easy, easy to implement, easy to work with. With all of that being said, we are very happy to announce that our best anticipated outcomes were achieved, and I'm going to pass it on to Zachary to talk to you about that.
So, in order for us to have met our anticipated best outcome, there was a few challenges that we need to overcome. First, we need to understand the hardware and figure out how we were going to communicate to the system. We would then need to communicate to a single site and learn how to read and write information to them. Once there, we could talk to the eFuse and eLoad, known as the electronically controlled fuse and electronic dynamic load. We would then need a GUI, a graphical user interface, to manage and control all of these features. So first, the hardware. We first needed to understand I2C communication. This is because all the devices on each site communicate over I2C. We decided to use a microcontroller, an Arduino Mega, for this task. And that way we can communicate between each neighborhood and the computer. From there, we could see everything connected to the I2C bus and start site communication. So the first thing we learned is that each device needed its own unique address. We had a 9-address limit, so to get around this, we had to learn how to use the multiplexer. This allowed us to talk to the same device on a different site with an identical address. It actually made it easy to expand to all 60 sites because the same set of addresses could be stored on every single microcontroller. And from there, we were able to implement full thermal control and start talking to the eFuse. So the eFuse is essentially an electronic kill switch that cuts off a site from power in case of a fault. So we implemented a fault management system that would turn on the eFuse in case of overheating or any other fault that's triggered, then displays that fault to the user. Controlling the eFuse was as easy as turning a single pin on from the Arduino. Last was the load. So the eLoad is one of the most crucial parts of the system because it's what sets the load current on the voltage converter. And that's what allows you to stress test these devices. So we had to learn how to control the digital to analog converter and program it using the GUI. Once implemented, you can set the load current with as easy as a single press of a button. This removed the need to do it manually. Tyler will now talk about the GUI itself.
To achieve our anticipated best outcome, we needed to integrate the given hardware with a user interface. The first notable screen of our GUI is the Site Monitoring tab. Its purpose is to display all the sites on a single screen, showing the current temperature, current fan speed, and any faults that may have occurred. Any site that has a fault is easily identified, and double-clicking on the panel brings up the error code. In addition, each individual site has is mapped to a unique site on the hardware. This allows the user to easily identify which site needs attention on the device itself. And finally, the system is robust enough to where we don't need every site to be functioning in order for the system to work. This entire neighborhood is faulted because there's no microcontroller connected, and the information is simply ignored. The second important screen is the site view, of which there are 60, one for each site. This screen shows all the logged information from the test for this specific site. It shows the exact time an error occurred, as well as the temperature and the fan speed at every read. This can easily be exported to an Excel spreadsheet for further data analysis. The most important part of this entire GUI is the control panel here, which allows the user to set the input, the temperature to regulate the system at. What this will do is it will adjust the fan speed on the site to regulate all the temperatures on the entire system to be running at exactly the same temperature. The fault monitoring tab is used to display any fault that has occurred on the site and neighborhood, as well as provide a brief description of the cause. And finally, the read interval can be set to control how much data and how often data is being read. As Infineon continues work on this system, it will become much more useful to them. The framework we have provided is only the first step in a fully functional and versatile testing environment. They will need to download the interface that we have developed, which will require downloading the interface and plugging everything in. In addition, there are many advanced tests that are done on these devices, which will require both hardware and software updates. From the results of these tests, the software can be further developed to provide rudimentary data analysis of the results collected. And finally, the framework that we have provided is functional, but there are many improvements and advancements that will improve the efficiency and usability of the system. So with that being said, we'd like to thank all the people who have assisted us in achieving our project. Thank you.